In this shorter video, we're going to look at the JK flip-flop in particular and how it improves on the SR flip-flop in the previous video. So why do we need a JK flip-flop? Well, there's issues with the SR flip-flop. One is that you can easily put it into an invalid state by having two high inputs with a NOR gate, with two NOR gates, and an invalid state with two low inputs with two NAND gates. But there's also the possibility that the SR flip-flop might enter what's known as an uncertain state. And this is when the pulses don't arrive at quite the expected time. If you think about computer systems, they run at millions of pulses per second. So, it's quite possible that an uncertain state can be entered. And so to prevent this, what we need to do is introduce a clock pulse, which synchronizes the inputs. And a JK flip-flop is an example of a logic circuit that uses a clock pulse. So if we start with a NAND SR flip-flop example here, with the JK flip-flop we're going to introduce a clock pulse, but we're also going to introduce two other NAND gates along the outside edge. And instead of S and R, we're going to have J, and we're going to have K as our inputs. But AND gates need more than one value. And so we're going to have the clock pulse as well. But there's a third part to this yellow NAND gates. The value of Q negated in the SR flip-flop, you can see it was passed into the other NAND gates, and Q was passed then into the sort of reset NAND gate. But with the JK flip-flop, Q negated is actually passed all the way back as a third input to the J NAND gate. And the Q value is passed all the way back as a third input to the NAND gate for the K. The reason for doing this is so that we can utilize J and K input values slightly differently. I'm not going to draw the full truth table for the JK flip-flop because you don't need to know it, but the four states that you do need to know about are: if J and K are 0, both inputs are 0, and then the clock pulses, that sets off the AND gates and feeds into the regular SR flip-flop, if you imagine. As those values pass through, whatever Q was previously doesn't change. But if J changes to 1, it's pulsed to 1, and the clock pulses and K stays at low, then Q will always become 1. Similarly, if J is 0, but K is pulsed to 1, and then the clock pulses, then Q will always change to 0. And the last state is that if both J and K are 1, and then the clock pulses, previously in the SR flip-flop we would have an invalid state, wouldn't we? But in this logic circuit, whatever the value of Q was is negated. So you end up with Q negated, okay, or it toggles. And they're the four states that you really care about with the JK flip-flop.